We now move on to types of solids. So up until now, we've just basically been saying solid, liquid, or gas, not really going any further than that, right? But we can actually indicate what kind of solid we're looking at depending on what the molecule is. And so first of all, we can actually classify solids into two main groups, and that is crystalline solids versus amorphous solids. So amorphous solids are solids that are going to lack geometric structure. If you were to take a look on the right side, you can see that that lack of geometric structure doesn't look too reassuring, right? It doesn't look very stable. And so these types of solids are, as you probably can guess, are going to break very easily. An example of an amorphous solid would be glass. Glass, if you were to drop on the ground, it would shatter instantly. Whereas a crystalline solid is a solid that is going to contain a particular geometric structure. And what composes that could be atoms, molecules, or ions, depending on what it is we're looking at. So amorphous solids don't really get categorized any further than that. They're simply lacking that structure. But crystalline solids can actually be classified into 4 different types of crystals. So the 4 different types of crystals that solids can be, crystalline solids that for that matter, can be molecular, covalent, ionic, and metallic. Right? So I'm going to do my very best. This is a one screen that kind of has everything all in one chart. I'm going to do my very best to try to make this as simple as possible. So first of all, let's compare covalent and metallic to molecular and ionic. Okay, so the reason why I'm categorizing them like that is because, generally speaking, they fall into these 2 categories for this particular reason. So if I were to look at molecular and ionic, these are going to be ones that are essentially compounds that are held together in a solid structure. And we'll go through some examples, but that's how you can tell those two. Versus you've got covalent and metallic. These are held together, or these are essentially atoms that are held together to create a solid. And once again, like I said, I'll show you examples, but that's how you can separate those two into 2 main categories. Now, let's go a little deeper. What is it actually that is holding a molecular crystal together? What holds a molecular crystal together are London dispersion forces, dipole-dipole forces, and hydrogen bonds. What's another way of saying that? Intermolecular forces. So it's molecules that are held together by intermolecular forces. That's actually what holds the structure together. We'll come back to that in just a moment. So that was molecular. Let's look at ionic now. So ionic are those electrostatic attractions that are holding the particular ions together. So essentially, when you see an ionic compound, such as salt, right? NaCl solid, that's what's holding that together. It's an ionic crystal because it's an ionic compound. Now let's contrast that to, let's look at covalent. So what holds the atoms together in a covalent crystal? You may have guessed it, a covalent bond. But the key thing is that it's the same atom. It's the same atom over and over again. No different atoms, it's just one atom, but a bunch of them are all held together by covalent bonds. Very strong. And then a metallic crystal is also the same atom, but it's metal atoms. It's held together by what we call a metallic bond. Now, what is all of that? Let's kind of look at some properties and some pictures, and then we'll do some examples. So over on the last column, you can see that it's talking about some properties. So molecular compounds tend to be fairly soft, low to moderately high melting point, just depends, but very poor conductors of heat and electricity. They do not conduct very well. Covalent crystals are very hard because of that strong covalent bond. So that also means very high melting points. These are also often very poor conductors of heat and electricity because there's nothing to carry the charge. There's no ions. Ionic crystals are hard and brittle. They do have high melting points because of those strong ionic bonds, but these crystals are also going to be poor conductors of heat and electricity, because an ionic crystal will not conduct heat or electricity if it's in the solid state. It has to be liquefied, or it has to be in the aqueous phase. And then finally, metallic crystals. It honestly depends. Some metals are soft, like sodium. Solid sodium you can actually cut with a butter knife. Or they can be very hard. Gold, like pure gold, is very difficult. You're not going to cut that with a butter knife. So that obviously means low to very high melting points. It just depends. But here's the thing. They are excellent conductors of heat and electricity, and that's because metallic crystals have electrons that are able to move. Also, as a reminder, metals, metallic bonds, are malleable and ductile. You can flatten metals into thin sheets or stretch them into thin wires. Let's take a look at some pictures, because pictures, to me, I'm a visual person, I like pictures, so they kind of help explain why the crystals are the way they are. So right here is, this first one is going to be a molecular crystal. So you see, you've got molecules, all kinds of molecules. But what's holding them together? Those lines represent intermolecular forces that are holding them together, right? So an example of a molecular crystal would be like solid water. We would call it ice. So water is a molecule, but those water molecules in ice, what holds them together are the intermolecular forces, the hydrogen bonds, all of that, right? The second crystal is the covalent crystal. So it's very, very tiny, but you see how all of these are the same color? That indicates they're the same atom, but they're being held together by something, and that something that we've talked about is the covalent bond. An example of this would be like carbon. Now normally we would, that's a terrible S, there we go. Okay, I'm just going to rewrite that because that was awful. Let me give myself some more space here too. So solid carbon. Well, solid carbon actually comes in various forms. It could come in diamond form, it could come in graphite form, but solid carbon is an example of a covalent crystal. Saying solid carbon, though, because carbon has many allotropes, which remember is different forms of carbon, it's actually not enough to say solid. So that's why a lot of times you won't see solid. It'll actually say the form, like such as graphite, or you might see diamond, because you have to specify. But it's all carbon atoms. They're just held together by a covalent structure. All right, the third one here, okay, you can see that, you got that solid structure, but there's two spheres in there, right? They're geometrically put together, but there's two spheres. The two different colored spheres indicates the cations and the anions. So we saw this structure at the beginning of topic 5. Because you have different color spheres in there, that indicates that there are different ions, positives and negatives, and so that's going to be your ionic crystal. Finally, what is a metallic crystal? If you think about like a gold bar, a solid gold bar where it's all gold atoms, what's holding those gold atoms all together? Well, a metallic bond, yeah, but what is a metallic bond? It's where all the atoms, so in this case gold, we'll say, all the gold atoms, they give up their electrons. So those giving up electrons are all these little tiny circles that are shown there. So they give them up. It's called what we call a sea of electrons, or delocalized electrons. Essentially, all those electrons just zoom around, and that's actually what keeps everything together. Those fast-moving electrons actually acts as kind of like a glue that keeps everything together. So those are the 4 crystals and their properties. Let's do 2 examples that will actually be samples of what you might see on an exam. So first of all, let's just do some pictures. Based on the 4 pictures shown, what kind of crystal would it be? So if I were to look at letter A, I can see you've got these molecules. You see molecule, even this is a molecule. But then you've got this yellow dashed line, and I'm not going to circle all of them, but these yellow dotted lines in between the molecules. So you have molecules that are held together by these dotted yellow lines, which, remember, those stand for intermolecular forces. So letter A would be a molecular crystal. Let's look at letter B. Now letter B, you've got these positive circles, and then you got these little negative circles. Now it might be tempted to think this is an ionic crystal. You think, okay, the positive is the cation, the negative is the anion. But do you see how there's really like no geometric structure? Because ionic crystals have geometric structure. This doesn't look like the negative circles are in any way, shape, or form put there in a pattern. So those negative little circles actually represent electrons that are all zooming in and out of these positive particles, which would actually be metal atoms. So letter B actually stands for a metallic crystal. If we take a look at letter C, you can see letter C, it's the same atom over and over and over again, but they're all held together by this solid line which represents a covalent bond. So this is a covalent crystal. And finally, we look at this letter D structure. We can see there's two different substances because there's different colored spheres here, but there is a geometric structure. So what do you think those two different colors stand for? Different ions. This would be an example of that ionic crystal lattice, or just simply an ionic crystal that we learned about in topic 5. Another example that you could possibly see is something like this. Maybe I give you the formula, the chemical formula for a substance, and ask you what type of crystal would it be expected to form if it was in the solid state. So the first one is aluminum. Well, notice it's a single type of atom. Specifically, it's a metal. So this is going to form a metallic crystal. So solid aluminum is held together by metallic bonding. If I take a look at the second one is a compound. Specifically, it's an ionic compound. Sodium and nitrate are cation and anion respectively. So because it's an ionic compound, it must be an ionic crystal. Carbon dioxide is another compound, but it's not ionic, it's a molecule. So this would be a molecular crystal. And then finally, S8. So it's 8 sulfur atoms all bonded together. Since it's the same atom, it's one atom, but it's not a metal atom, this must be held together by a covalent crystal. Alright, so that wraps up section 3, which is talking about solids. We'll see you in the next section.